Our next speaker is Taweewat Somboonpanyakul, who's from MIT, and his talk title is Galaxy Clusters and AGN Feedback, the clusters hiding, sorry, oh dear, the clusters hiding in plain sight survey, which is CHIPS. Please go ahead when you're ready, Taweewat.
Okay. Yeah. So can I start now?
Well, yeah, we're a tiny bit. We're about a minute ahead of time, but I mean, I guess either you can start now and we'll be a little bit ahead, or you can hold off a few.
That's fine. I can start. Thank you. Okay, I guess today is the 15 and the 16. Okay. Yeah, thank you for coming to my talk. So I'll have a 15-minute talk here, and the title of the talk is a Galaxy Cluster and AGN Feedback, and so my thesis project is called the Cluster Hiding in Plain Sight Survey, or the CHIP survey. Okay, let me start. Okay, since we are in the Galaxy Cluster section, I'm probably gonna go through this pretty quickly. So what is a galaxy cluster? So it's basically the most massive gravitationally bound object in the universe. It consists of many galaxy members, like every speaker that we talking earlier today. So each one of these large galaxies here are a member of one giant galaxy cluster. It had a central BCG, or the center galaxy at the center of the galaxy cluster, which is usually the brightest and the biggest one, and it's usually located at the center of the galaxy cluster. It contains an extremely hot gas, so 10 to the 7 Kelvin degree gas inside the ICM, and the ICM is the intra-cluster medium, so that is the blue emission here. And the reason that it's very interesting to look at the X-ray in the ICM is because many major events have imprinted in the X-ray morphology. For example, it's very easy to see the ongoing merger inside X-ray morphology, because in the X-ray you can clearly see the bullet light shape inside a galaxy cluster. And all this disturbed morphology is very easy to detect with the X-ray. And you can also see sloshing. This sloshing is also a signature for a merger event, but it might be a little bit afterward. And those can also be detected with the X-ray. And also bubble with the giant cavity that you can see from just looking at the X-ray. Okay, before I talk too much about my project, let me talk about one problem that we have in galaxy cluster. So it's the suppression of star formation. So if you look at this plot here, before I talk about that, so I'm talking about the ICM. So as the gas are radiate out the energy and all the gas are giving out, then the gas will actually become much cooler. So that means the gas should actually lose its energy as it radiates out the X-ray emission. And as that gas radiates out, and then the temperature of the gas should come down, and it should eventually form star in the center of the galaxy cluster. However, if we look at the distribution of the star formation rate compared to the cooling rate of the galaxy cluster, you can see that it's not actually peak at 1 or 100%. Instead, it peak at 0.01 or 1%. That means only 1% of the gas that are radiating out into the X-ray can actually cool into the star formation, into a star inside the center of the galaxy cluster. And we call that the cooling flow problem. And that, so because we expected to see all this cooling flow happening inside the galaxy cluster, which did not happen. And the solution for that is AGN feedback. And the basic idea of AGN feedback is the AGN inside the BCG, so the brightest galaxy inside the galaxy cluster, is energy output from the AGN have enough energy to actually counteract with all the cooling that's happening into the outskirts of the galaxy cluster. So for example, there can be an AGN jet and cavity and all these high energy event from the AGN. Okay, but it's not just not every galaxy cluster look like that. So the Phoenix cluster is the most famous exception to the rule. So instead have extremely low star formation rate. The Phoenix cluster have extremely high star formation rate at 600 to some people say 800 solar mass per year, with a strong cool core in the center, and it's also located in a relaxed morphology without any merger event happening recently. Okay, so every people will always ask the question, what happened to the Phoenix cluster? Why is the Phoenix cluster very different from any other cluster that we know of? And one way to answer to ask the question is how rare is the Phoenix cluster? So how often can we expect to see Phoenix-like cluster in our universe? And okay, so that lead me to the project that I'm working on with my advisors called the Cluster Hiding in Plain Sight Survey, or the CHIP survey. And the point of the project is try to find a Phoenix-like cluster from the Xray or Sky survey. Before I talk about CHIPs, I have to talk about Phoenix a little bit. So here is what the Phoenix look like with the low sat observation. Basically, it's this point here. So every time people look at the low sat data, they call it a point source object because it looks just like a point source without any extended emission. But if you actually look at it with Chandra in 2012, you can see that it's clearly a really bright point source in the center, just like low sat said. But it have this extended emission that you can see much more clearly in Chandra compared to low sat. And with even more data with Chandra, you can see that location in the center actually have a signature for the bubble that you can actually clearly see now with the Xray data. Okay, so now the question would become, how many of these so-called Xray point sources are in fact a galaxy cluster? So, okay, so to start the project, we basically just look into Xray or point source catalog. So each one of these objects here are the Xray point sources that are reported in the low sat catalog in, I think, 1990s. And then I basically go look at each one of them and try to match it with all the other Sky survey. So from the Xray low sat point source catalog, then I will match it with the mid-infrared, near-infrared, and radio. And we only pick the brightest and brightest one for this sample because we would like to follow up with all the objects in the entire sky. So here is the CHIP survey. So here are all the sample that we have and then we try to follow up with optical. So every blue point here are already being followed up with Sloan, and the red point here are by Pan-STAR. But since I started my project 4 or 5 years ago, we don't have a DS yet, or it's still in process. So instead, I'm using PISCO or a new instrument that are located at Magellan Telescope in Chile. So I do individual observation of this green point here. It takes about 5 minutes per object, and that covers the entire southern sky. Okay, so here is the main result from the paper. So here is Lichner redshift plot. So the Lichner is basically the number of galaxies in each candidate, and the redshift is how far away the cluster. And everything above the blue line here we call it a galaxy cluster candidate, where most of them are known galaxy clusters. So all the orange point here are known galaxy cluster from the Phoenix cluster, Abell 1835, Zwicky 3146. And all the blue point here are not, they're previously unknown. So now we actually follow up with each one of these with Chandra data. Okay, so before I talk about so here is the main result from the paper. So now we can answer the occurrence rate of Phoenix-like cluster. So basically, we found that there are about 10 galaxy clusters above the blue line, and with the Xray cluster sample that I have been doing with the low sat survey, is that there are like Reflex, EBCS, and MAX, and there are about 460 clusters found with all that 3 cluster sample combined. And that means the occurrence rate is about 2%. So how rare is the Phoenix cluster? Is pretty rare at 2%. And okay, so what does 2% mean? So it could mean 2% of the cluster have this phoenix-like feature all the time, but instead what we're thinking is it actually all the cluster have this phoenix-like feature of a high star formation rate and starburst galaxy about 2% of the time. So just a quick diagram. So basically, every galaxy cluster have to go through this phase of high star formation rate, but only 2% of the time. So that's why we only see 2% of the sample with this kind of feature. Okay, so what is the implication? So one of the implication is about chaotic coaccretion. So instead of this feedback happening all the time, the feedback actually have some lag time here that result into a short life brightening of the agent. And so basically what happening is the agent become active, and there is some delay time between when the agent active and then when the jet actually created and then sweep out all the material. And those delay time is probably happening in about a few percent compared to the lifetime of the agent activity. And that few percent is a result from what we see with the Phoenix cluster and the other cluster that we detected with the chip survey. Okay, so I think I have 5 more minutes. So I want to talk about one more cool galaxy cluster that we found with this sample. Is chip 1911 plus 4455. So here is what it looks like. So the lead chip is about 0.58 or no 0.53 or something. Okay, so here is what it looked like in optical with pan-star. So this object have been detected first with pan-star that we use, and you can see that there are a lot of red galaxy here that you can clearly see in optical, but the central galaxy here is actually not red. So it's actually whitish and have this like weird tail coming out. So it could be a weird star forming galaxy. But so then we actually go and get additional data from Hubble. So here is what the Hubble data look like. So now this bluish galaxy actually normal elliptical galaxy, but with this extreme filament in blue color here, that you can also see extended up to this part in the north part of the sky. In the northern part of the galaxy cluster, and the center is located at the center of the galaxy. So if we zoom out here, and here is the X-ray emission, so you can see that the X-ray emission is not really relaxing, so it's actually in the disturbed morphology. So we're thinking that this galaxy cluster should be in a merging period or in the merger cluster. Okay, so why is this galaxy cluster is interesting? The first thing is so we follow up with the extreme with the optical spectrum, and then we found that it have a extremely high star formation rate. So here is what the spectrum look like, and here is the O2 emission line. You can see that the O2 emission line is actually clearly, it's really obvious you see in the 2D spectrum, and it's have a really high peak here. So from that spectrum here, we can convert the star formation rate to be about 140 to 190 solar mass per year. And we can also estimate the star formation rate from the mid-infrared band. And that gives us about 140 solar mass per year too. So those two are consistent. Okay, so here is what a galaxy cluster look like in X-ray. So we get additional data from Chandra. That's the 30 kilosecond of Chandra data. And it have been adaptively smoothed. And you can see that there's a cool core in the center, but one can say that there might be 2 cool cores instead of 1. And that could be the signature for the merger event, and also the highly disturbed morphology in a large scale. Okay, so when I put everything together here, you can see that so here is the slit location, and you can see that the peak of the X-ray in the peak of the X-ray in the cool core region here is co-located with the bright galaxy inside the galaxy cluster with the filament. And the second peak here, one can say that it also have some blue filament here happening here. So there could be some interaction between the two filament-like structure here and the X-ray. Okay, so let me concluding my talk. So what did we learn with the chip survey? So the chip survey tells us that the rarity of these extreme cases like the Phoenix cluster told us that it's probably the chaotic accretion that could be a mechanism for the feedback. And the feedback have a lag time of about 2 plus or minus 1% of the total lifetime of the galaxy cluster. And then we also see that this survey also found a new mode of cooling with the chip 1911 plus 4455. So that means there is a massive starburst, so like an extremely high star formation rate inside emerging galaxy cluster, which is unlike any galaxy cluster that we know of, including the Phoenix cluster. And that's it for my talk.
Okay, thank you very much for an interesting talk. Let me first of all go and check and see whether there have been questions posted. Is your constraint on the AGN duty cycle consistent with the occupation of X-ray bubbles in cluster cores? This is from Konya Zhang.
Good question. So okay, so the question is it consistent with the occupation? So okay, so I think there are a lot more bubble that we can see in X-ray compared to the 2% here. So we think that so the duty cycle of the agent in the X-ray cavity might be difficult to interpret because it's because we're thinking that maybe the agent is not completely shut off. So as the galaxy cluster agent become so when I say it's become non-active or become this kind of activity, there could also be some activity going on with just much lower. Okay, I don't know I answered that question correctly, but yeah, I don't think it's consistent, but then I don't think it's a problem yet because the duty cycle that we see in the cavity is not the same thing that we see here with the lag time, with the Phoenix like property.
Yeah, you showed a diagram earlier. I think the thing is it was the fraction of the time the AGN is off that was the bumps in that diagram. Yeah. Mm-hmm. Okay, thanks. And there's another question from Emily Moravec. Says, interesting work. I may have missed this, but could you talk about how you selected your CHIPS clusters again? How is your selection method different from other cluster surveys?
Okay, good question. I can go. Let me go back actually. So okay. So so the starting point is very different. So instead of focusing on known X-ray cluster, like X-ray clusters sample, we actually start from point source catalog. So all of these dot here are X-ray point sources that we detected with LOSAT. But then each one of these point sources, I mean, most of them are probably not a galaxy cluster. Most of them are probably just an isolated AGN. So I'm not saying that all of these are galaxy cluster candidates, but my project is try to go and look into these and see which one of these are misidentified galaxy cluster. So so the short answer is instead of looking for extended X-ray emission, I look for a really bright central point source emission, and then try to find which one are those that could be extremely bright agent inside the galaxy cluster. And that brightest like basically masks out all the extended emission you can see in the X-ray.
So great. And just as a matter of interest, it is remarkable that you found another candidate that's like Phoenix, or at least somewhat like Phoenix. Mm-hmm. I was just wondering if you could just say a little bit more about the properties of that cluster. I mean, for example, do you have a temperature for it?
Yes, we do have a temperature for it. Okay, I can show you. Sorry, there's a lot of sorry. Here. Oh no. Too many pictures. Oh, here. So here is what the temperature look like. Okay, so the temperature is a normal looking cool core cluster. So the central temperature is about 4 keV, and then the peak is about 10 keV. So and then the cooling time from combining the density and the cooling time and the temperature get a cooling time about like 100 megayear, which is much lower. So we think it's a typical strong cool core cluster. But the different thing about this galaxy cluster compared to any other galaxy cluster is that it's actually located in a highly disturbed morphology. So it's pretty interesting that these cool core cluster are inside a disturbed morphology. I see.
Okay. All right. Well, thank you very much for another interesting talk. And we should start to move on to the next speaker, who is Victoria Butler. And just